Every time we open a language model, we start from scratch. No matter how many times we've explained something before, each interaction is independent, as if it doesn't know us. This isn't just a random bug, but a direct consequence of how they're designed. They train once for months on massive amounts of data and then remain frozen. They don't incorporate anything from our daily interactions with them. Meanwhile, we're seeing that making them larger no longer yields dramatic quality improvements. Costs rise significantly while improvements become increasingly marginal. So the problem is twofold. On one hand, models don't learn from experience, and on the other, their bigger is better approach is showing its limits. We need another strategy, or rather, several. We can imagine AI as a brilliant student with terrible memory. Every day it wakes up without remembering which exercises it did well, which ones confused it, or which explanations helped most. Each test is like taking the very first exam of its life. That's essentially what happens with many current models and the agents we build on them. They approach each task as if brand new, without leveraging past experience. In response, we now have two main approaches changing the landscape, one from Google, another from MIT, plus an intensive practice concept that enhances them even further. We can view these as complementary ways to help that student, providing a well-organized notebook and allowing them to rewire their brain so certain lessons become automatic. The first approach is Google's, and it's called Reasoning Bank. We can think of it as an external notebook where people not only record what happens, but transform it into general strategies. And the crucial thing here is that it doesn't just stick with what worked well, but also learns from its mistakes. A failure stops being noise and becomes a useful warning and something not to repeat. The cycle works like this. Facing a new task, the agent checks its memory and retrieves relevant lessons. It acts with that guidance. Afterward, a model evaluates the result, whether successful or not, and new memory items are distilled from that experience. Each one has a title summarizing the idea, a description of when to use it, and content with refined steps. It doesn't store specific clicks or complete paths, but strategy patterns that can be reused in completely different websites or environments. The quantitative results are promising in environments like WebArena. An agent without memory achieves only about 40 to 47% success, and when we incorporate the reasoning bank, the success rate rises to about half of the tasks solved, with increases of over 8 percentage points in some scenarios, plus a reduction in steps by about 16%. It not only gets more correct answers, but reaches solutions faster, avoiding unnecessary detours. On this foundation emerges another key piece: intensified practice, guided intensive training, known as MAP. The idea is giving AI more opportunities to practice the same task before delivering the final result. What's interesting is how the circle closes. A good memory ensures this practice isn't blind, but directed towards strategies that have already proven promising, and that practice produces higher quality experiences that further enrich the memory. Better memory leads to better practice, and better practice builds an even more useful memory. The second approach is from MIT, which is more radical, called SEAL, or self-editing language models, which are self-learning models. Instead of just using external memory, the model learns to rewrite its own parameters with the goal of generating its own training examples and update instructions. The SEAL cycle works like this. We give new information to the model and it proposes a self-edit, essentially a study plan for integrating that information. It applies this plan through a small fine-tuning process on itself and then evaluates whether it has improved or worsened. Based on the result, it reinforces or penalizes that type of self-editing and over time discovers which training procedures work best. The numbers show a significant jump in tasks like squad. Accuracy increases from 1/3 to almost half. In a comprehensive benchmark of abstract reasoning where the original approach with standard in-context learning achieved 0% success, the complete SEAL version has reached over 70%. Reasoning Bank has its own risks, primarily depending on the quality of stored memories. If an agent distills an incorrect strategy, that flawed lesson can spread to many future tasks. Additionally, proper memory index management is crucial to find relevant information, and the context window limits how these instructions can be injected. This adds to a shared challenge of interpretability in Reasoning Bank. At least the memories exist in natural language, allowing us to track what has been learned.